building ethical machine learning systems is paramount in today's AI-driven world. Machine learning engineers play a crucial role in constructing responsible AI, ensuring that these powerful tools benefit society without perpetuating or amplifying harm. Their responsibility extends beyond mere technical performance to the societal impact of their creations. The increasing integration of AI into critical domains like healthcare, finance, and criminal justice amplifies the urgency of ethical considerations. Unethical AI systems can lead to discriminatory outcomes, erode public trust, and have severe real-world consequences, from biased loan approvals to unfair hiring practices. Bias in machine learning is a systematic error that skews predictions or decisions, often leading to unfair advantages or disadvantages for particular groups. Sources of bias can be manifold, including historical biases present in training data, sampling bias where data doesn't accurately represent the target population, and measurement bias where features are imperfect proxies. Algorithmic bias can also emerge from the model's design itself. The ML engineer's role in building responsible AI systems is proactive and encompasses the entire machine learning lifecycle. This involves setting ethical goals, identifying stakeholders and potential impacts, mitigating risks through design, continuous testing, validation, and deploying with robust oversight. It's about embedding ethical principles from the outset, not as an afterthought. Practical approaches to detecting bias in data begin with thorough exploratory data analysis. This involves examining demographic distributions, identifying underrepresented groups, and analyzing outcomes by subgroups. Statistical tests, like chi-square tests, can quantify imbalances and determine if certain groups are adequately represented. Checking for coverage bias and data skew are also critical. Mitigating bias in data often involves preprocessing techniques. These include resampling, where underrepresented groups are oversampled or overrepresented ones are undersampled to balance the dataset. Another technique is reweighting, which assigns higher importance to samples from minority classes during training to reduce bias against them. Detecting bias in models extends beyond the data. It requires algorithmic inspection, such as feature importance analysis, to understand how features disproportionately affect certain groups. Algorithmic audits and impact assessments are crucial for uncovering hidden biases and understanding the real-world implications of the model's performance across different demographic groups. Tools like the What-If tool can also help by allowing engineers to test various scenarios and analyze impacts. Mitigating bias in models can be achieved through various strategies. Preprocessing techniques modify the data before training. In-processing methods adjust the learning algorithm itself, for example, by incorporating fairness constraints or using adversarial training. Post-processing techniques modify the model's predictions to ensure fairness after training. Adjusting the model's optimization function to penalize errors in a fairness-aware manner is also an effective approach. Evaluating fairness in AI systems involves specific metrics. Group fairness metrics ensure similar treatment or outcomes across different demographic groups. Common examples include demographic parity, which measures if positive outcomes are evenly distributed across groups, and equal opportunity, focusing on achieving the same true positive rates across groups. Equalized odds further demands similar true positive and false positive rates for each group. The disparate impact ratio compares outcomes between groups, with ratios below 0.8 often raising legal concerns. Model interpretability and explainability are crucial for building trust and understanding how AI systems make decisions. For complex black box models, this means being able to articulate why a specific prediction was made, which is essential for identifying potential issues like bias, ensuring robustness, and establishing causality. LIME, or Local Interpretable Model Agnostic Explanations, is a technique that approximates any black box machine learning model with a local, interpretable model to explain individual predictions. It works by perturbing a single data sample, feeding these variations into the black box model, and observing how the predictions change. A simpler surrogate model, often a linear model, is then trained on these perturbed samples, weighted by their proximity to the original instance, to provide a local explanation. SHAP, or Shapley additive explanations, is another powerful explainability method that provides a game-theoretic approach to interpreting model predictions. Based on Shapley values, SHAP attributes the contribution of each feature to an individual prediction, revealing not only feature relevance but also whether a feature has a positive or negative influence. This method provides a consistent framework for interpreting predictions, connecting them to fundamental game theory principles. Both LIME and SHAP can be practically implemented in real-world scenarios to enhance model transparency. For instance, in a loan application system, LIME could explain why a specific applicant was denied by highlighting the most influential features for that particular decision. SHAP values could similarly quantify the exact contribution of each feature to that denial. These techniques are vital during development for debugging and auditing, and in production to build user trust and facilitate compliance. Building ethical ML systems is an ongoing journey that requires continuous monitoring and a commitment to ethical considerations throughout the AI lifecycle. ML engineers are at the forefront of this effort, ensuring that AI technologies are not only powerful and efficient but also fair, transparent, and beneficial for all members of society. Their expertise is crucial in navigating the complexities of AI ethics and fostering a future where technology truly serves humanity.